All right, welcome everybody to today's webinar. It's my pleasure to introduce, we have of course the one and only Christopher Lilienstope and Gunjan Patel as well, who'll be talking today about CNI. So to give you some quick background, Christopher has extensive experience with networking, ranging from obviously here with larger companies, Metaswitch, Big Switch, Telstra, and of course we mentioned the IETF working groups that you chaired. Our guest today, Gunjan Patel is a software engineer here at Tigera, also extensive experience. And Gunjan, I understand you're getting your master's in computer science today, is that correct? So congratulations on that. With that, I will turn this over to Chris to kind of start us off about what this thing called CNI is and why we should be interested in it.
Sure. All right. Thanks, Mike. So I'm just going to spend a couple minutes talking about what CNI is and what the concept of a network API it is, what something like a CNI is. And then I'm going to turn it over to Gunjan, who actually has done quite a bit of work in CNI, and he'll sort of walk you through the specifics of CNI. So if we think back to the way we used to build networks and data centers, we used to rack and stack. You take servers, you wire them up into switches, you connect the switches to routers and firewalls, and that was a function that when you'd stand up a new application, you'd stand up a new server, it was all part of a physical commissioning process. And all of those things were fairly manual processes. So it didn't really matter if it took a day for the network engineers to program the switches and get the rules in the firewall and basically do the networking necessary to bring that new node up and running. So that was a very manual process, but it worked. As we started moving to virtualization, where now computers could spin up workloads, and we could automate that process. And VMs weren't particularly fast, but they were definitely much faster than a rack and stack operation. So you might have create a VM image, and 15 minutes later or an hour later, it'd be up and running, and would need to be networked. And it might only exist for weeks or months, etc., rather than the years of a server being racked in a rack. So you needed some way of managing those VMs. So we came up with orchestration systems. That could be VMware, vSphere, that could be OpenStack, that could be a number of other systems that were out there, CloudStack, some of the others that were out there to manage VMs. And these are the things that are now creating servers in your network. They happen to be VMs, but they're still servers. So you had two options. You could either have the orchestrator stand up the VM and then still have the networking guys go program things, or you could have the orchestrator also configure the network, the virtual network. So two things came out of that. We started creating software-defined networks, SDNs, that could be driven in a software manner rather than plugging cables and configuring routers directly by typing on CLI. And two, we had to create some mechanism for the orchestration system, be it vSphere or OpenStack or something else, to talk to that SDN and tell it what kind of networking that server needed or that service needed. So we created a number of mechanisms to do that, and I'll pick on my favorite one, which was Nova Networking in OpenStack, and then Neutron as a follow-on to that. The problem for those was networking guys like I were the ones who created them. So networking guys think in terms of subnets and routers and switches and firewalls. So what we did was we created an API that was based on routers and switches and subnets and networks, etc., and it had very network-centric primitives. Which also meant that they were very prejudiced as to the type of network. If I was doing this as an enterprise network, I thought of these as L2 infrastructures. I create VLANs, and I'll create segments, and I'll connect those to routers. So what we did was basically unintentionally created a set of APIs that almost dictated the type of network that you could build. And we're also very network centric, which is not the way necessarily all operations folks think, or certainly developers don't think is in the way a network engineer does. It's probably a good thing. So there was a bit of an impedance mismatch there. And again, they force certain behaviors and certain network constructs, when really what you need to do is say, this workload is being created, it needs to be connected to a network. The other thing we did with those APIs is we tried to conflate security and connectivity. So in the old days, security was basically stick everything needs to talk to each other on the same network and then stick a firewall between the different networks. As you look in some of the blog posts I've done recently, that model doesn't really work as we get to very high scale and very rapid churn. So we also not just put connectivity in, we put security or isolation characteristics into these APIs. It worked. It was fragile, and talk to anyone who's run OpenStack network what they feel about Neutron. Sorry for you Neutron fans out there, but let's just call it was a good first effort. Containers come along. Containers now have life cycles of minutes or hours or seconds or maybe days versus the weeks, months of a VM. There's a lot more of them. It's a much more dynamic environment, but the requirement's still there. The orchestrator has to be able to orchestrate the network as well. So there were basically two approaches that were taken in the community. There was a revision of the more classical approach to SDN and network APIs, where we took the same kind of networking constructs and tried to make them container friendly. And there was a group of work around that. And then in parallel, there was a group originally came out of CoreOS that said, we really shouldn't be thinking in terms of network. We should be thinking in terms of basic connectivity. Let's forget the security for right now, and let's just get pods or containers networked. So let's do a really simple construct that software developers, et cetera, would understand. What came out of that effort was this thing called CNI, or Container Networking Interface. And the Container Networking Interface is simply a way for the orchestrator to tell a SDN or another networking construct that exposes the CNI interface that it wants to connect a workload to the network, or it wants to remove a workload from the network. And that's all CNI is. And Gunjan's going to walk you through that here in just a couple minutes. CNI then was picked up by Kubernetes as its networking infrastructure API, and many other container orchestration systems and PaaS systems have now also adopted CNI. So Mesos, Cloud Foundry, Docker, Rocket. I've lost track of how many people are now implementing CNI, but pretty much it's become almost the industry standard for networking APIs, especially in container environments and PaaS environments. Now, I said we parked security. Doesn't mean we don't need to do security and isolation in the network. So what the Kubernetes community has done is now said that security policy or network policy is another API. Let's not make CNI complicated. One of the ways you do something at scale, or you build a platform for scale, is you loosely couple things. You make them as simple as possible, and you do it as well as possible. And all of those things argue against trying to put a whole bunch of stuff into one API or one mechanism. So CNI does one thing well. It connects workloads and removes workloads from the network. Another mechanism, which in Kubernetes is the network policy API, does okay, now the workload's connected, what kind of network policies, what kind of isolation, who should it be able to talk to, who should be able to talk to it, is now enforced. And that's enforced via a mechanism that's signaled via what's called the network policy API. And then different network providers that plug into these APIs may just plug into CNI, may just plug into network policy, may plug into both, like Calico does. So Calico listens to the open source project we do, And there are others that listen to this as well. There are other network platforms that do the same thing, that will listen to CNI for connectivity requests, and will listen to network policy API for network security configuration information. Do one thing, do it well, loosely couple it with everything else, and that's how you get to scale, and that's how you get to be able to deal with high churn and like I said, and high scale. So that's really the trick here. Keep it as simple as possible, keep it loosely coupled. Now that I've gone on more than I should, let me turn it over to Gunjan and let him show you how simple this is and how clean and actually fairly elegant CNI is. So Gunjan, I'll turn it over to you at this point.
So as Mike said, my name is Gunjan. I'm a software developer at Tegear here, and we're going to be walking through CNI, overview of CNI, and try to zoom into how it works and take a few example CNIs. So first of all, the outline here is really briefly, I'm going to talk about how containers are made, what CNI is, then we'll try to do a CNI by hand, and then Calico CNI internal. So let's get started. So very briefly, how containers are made. They are made up of namespaces. There's various namespaces, C groups, and layered file system that makes a container. One thing to keep in mind here is network namespace, because we'll be using this in the next few slides. And if you're interested in more about container internals, I made a fun little project making containers from scratch in Go. That's at this link below. So what is CNI? Now, right now, if you go on GitHub, go to this URL. This is github.com/container networking. You'll find two repos. One is called plugins and one is CNI. The CNI is the main repo where you'll find the CNI specs, the CNI specification. This repo also has APIs and libraries for orchestrators and plugin authors to use. If you go to the plugins repo, you'll find a bunch of simple sample plugins, such as Bridge, Host Local, Point-to-Point, Flannel, etc. Now let's look at CNI from 9,000 feet. At a very high level, your orchestrator calls the CNI plugin. Now CNI plugins implement the CNI specs. If they follow the CNI specification, any orchestrator can call any CNI plugin with that standard interface. And then the CNI plugin can program the container or network namespace. Think of it as a USB interface. It's a standard, simple interface. Right now, if you go and buy anything that's USB, you don't have to make sure that this works with that. If it says it's USB, this time it works. Now, let's try to zoom in a little bit more. CNI from 5,000 feet. Now, in here, the orchestrator typically uses the CNI libraries, which can be found from the CNI repo. CNI plugins usually take two main commands, add and delete commands. There's a third one that was added recently called versions command. So orchestrator calls CNI plugin to add or delete a container, and then CNI plugin will network the container. So typically you need a network definition that's a JSON network definition like this one for cut. And then when the orchestrator calls the CNI plugin, it passes some arguments specific to that container. So you can see it goes and networks a container. Now, as you can see in this diagram, you can have one container part of two different networks or more than one networks. Now, let's try to do this by hand. So I'm going to walk you through a small demo. All right, so here I have one Ubuntu VM. Right now, I don't have any container runtimes installed here. If you see Docker, it's not there. What we'll do is we'll create a network namespace. Remember I talked about what network namespaces are? They are part of container runtime. Container runtime uses network namespace to isolate the networks. So I'll create a demo namespace. Now, we are still in the host namespace. If I do ifconfig, we only have each0 interface here and loopback. So here we'll watch the host namespace for routes and interfaces. And in this window, bottom right corner, what we do here is we're watching IPNetNS exec, which means we are executing inside the network namespace, ifconfig, and route-n. So we'll be watching the routes in that namespace. Right now, there's nothing in that network namespace. So you won't see anything right now. So here, I downloaded a bunch of sample plugins from the CNI plugins repo. Let's try to call this plugin PTP. It stands for point-to-point. It's a CNI sample CNI plugin. So right now, if you call it, it says it needs a CNI command. So let's pass it a CNI command. Equals, let's say, version. Call it, right now it's a sitting because it's expecting the network definition from standard in. As Christopher said, CNI is a very simple interface. All it's using is environment variables and standard in to get its configuration. So let's see, I have a configuration here. You can see, it's a very simple configuration. It has CNI version 0.3.1, which is the latest CNI spec version. Name of the network, I'm calling it DemoNet. Type PTP, that's the binary name that we're calling. It also has an IPAM section. So there's two kinds of CNI plugins. One is the one that does networking, and the other kind is IPAM. And here we are calling host local IPAM plugin, which is another sample plugin from the CNI plugins repo. And the subnet is, we just select the subnet, and host local IPAM will take care of assigning IPs. So now let's try to run that command again. But this time we will feed it the config from standard in. Now we see the CNI version it has currently, and all the CNI version it supports. So now let's try to run the add command. Remember I said CNI takes two main commands, add and delete. Add means network the container, delete means remove the container from the network. So if you run this, it's complaining that it doesn't have all these environment variables that you need to pass as an argument. So let's try to pass those in. In the interest of time, I will just find the command I had before here. So as you can see, CNI command is add. CNI netns is the path to the network namespace we just created. And the CNI interface name, which is the interface that will be inside the network namespace, and the CNI path, where you will find the executable. So now notice on these two windows on the right side, when I execute, you will see it create two interfaces, one on the host side, one on the network namespace, and then link them together and add the routes. So there, I execute the command, and you can see it created routes, default route. And so here, let's take a look at the network namespace. It created the demo each0, it assigned it an IP 10.0.0.10. And when we executed this command, it gives us this JSON output, which is called the CNI result. IPAM returned that this is the address, IPv4. That's the IP that's programmed inside. This plugin also added default routes inside the network namespace or the container, if you wish. And this is the path it created on the host namespace, and it also added the route to the container. Now, if we're done, we would just like to delete this network container. So we just send it a delete command, and there, it's gone. It deleted the interface and routes. Now, let's get back to the presentation. So what just happened? I would like to show you visually what we just did in that CNI by hand. So we had root namespace, which is the host namespace. We created a demo NS. Then we had this network configuration on the host as a JSON file. Then we called the P2P plugin with CNI args as the environment variable and network configuration as standard in. And the plugin then creates demo each0 and with on the host network namespace, connects them, adds the default route inside the network namespace, demo NS, and a route on the root namespace. We did all that without any orchestrator or a container runtime. That explains how simple it is to use CNI. So what's new in the CNI world? So CNI recently released version 0.6.0. Make sure you understand the difference between CNI versions and CNI spec version. CNI latest spec version is 0.3.1, which is the specification version, which doesn't change that much. But CNI version, which is the libraries and plugins, that's the version I'm talking about, 0.6.0. So now in the CNI, we have plugin chaining support, where you can chain multiple CNI plugins. So your orchestrator can call multiple CNI plugins, one after another. One of the recent plugins that was added to the CNI repo was port map plugin, which can do host port for you. And port map plugin usually works with in chaining with another plugin, such as Calico. So when you have to do host ports, Kubernetes will call Calico CNI plugin and then the port map plugin in chaining. Then recently, a lot more CNI plugins were added, had IPv6 support. Now, we talked about this. Now, let's try to look at another example of CNI. Project Calico has a CNI that works with all these orchestrators. Let's take an example. So in this animation, we'll see the flow of what happens when you create a container in Kubernetes with Calico CNI. So Kubernetes API server calls the kubelet on a specific node and says, hey, schedule a pod. Then kubelet will create the network namespace for the pod, which you might know as the pods container or infrastructure container. And then it gets the reference to that namespace back. Now, kubelet will call CNI with the add command using the CNI API libraries. And Calico CNI implements the CNI specs, so it will just work. Then Calico CNI queries Kubernetes API server for labels and annotation if there's anything specific for that pod that we need to do. Then Calico CNI calls Calico IPAM, which also implements CNI specification. So it also calls Calico CNI with the add command. Calico IPAM then queries the IP address to a centralized data store, and if it gets the IP, it will return the IP address to Calico CNI. Now Calico CNI has all the information it needs to network a pod. So it will gather all that information and create a workload endpoint object in Calico data store for Calico to internally track the container for policy enforcement, etc. Now, Calico CNI will create a vEthernet pair inside the pod network namespace, ETH0 being the pod side, and Kali and some hash for the host network namespace side. It will add the IP address to the Ethernet on the pod, add a default route, then it will configure some sysctls on the host side, and now it will move the vEthernet pair where Kali interface goes on the host network namespace. And then finally, it will add a route to the container IP. There you have it. So that's what Calico CNI does whenever Kubernetes or any other orchestrator calls it. Then Calico CNI will say, okay, pod is network, and Kubelet will propagate it back to the API server saying this pod is network and this is the IP address. But yeah, there you have it. That's the very high level overview of what happens with the CNI and what's going on in the CNI.
That's pretty impressive. I'm just curious, like what you did the CNI, how long would that have taken if you wanted to like do that manually, if you wanted to install like the container environment or write, those implementations by hand?
Oh, that would take a very long time.
Okay.
One thing I would point out, though, is it did look like there was a lot of transactions going on there as part of the CNI network setup. That all transpires in a couple of milliseconds in all reality.
Yes.
It's a very, very fast set of transactions. So it looks like there's a lot of queries going on, but in 99% of the time, you can usually get your pods connected and networked within circa 10 milliseconds. So it's, and that includes propagating policy, a bunch of things we didn't talk about here. So this is really just a couple of milliseconds to make all those transactions happen.
Yeah.
Nice.
It's less than a second to do all this and enforce policy with Calico.
Yeah.
Oh, wow. And how scalable is CNI? Like with all that going on, all those transactions, is that something where it can be done a couple times and you're fine, or it can be done millions of times? Or...
Yeah, it scales pretty well because it's a very simple interface. Mm-hmm. So CNI generally works like it can never. So it's an executable binary. It can be called as many instances of that binary can be called at the same time as the orchestrator wants to schedule a pod.
And I think the other thing there, Mike, that's important is there's not a central controller here. You never saw a central controller that would end up, even if you somewhat distribute that, that does become potentially a bottleneck point. There is everything you saw there, all the CNI transactions were happening locally on the host. So if I've got 1,000 hosts, I have 1,000 different endpoints doing this only for the subset of nodes that are on those individual hosts. The only off-host transactions was the initial messaging from Kubernetes to the kubelet and the few dips that in our case we do into the Calico data store, which is also distributed. So there really most of the stuff is happening locally. That's how you get to scale in any system, is you do this in a horizontal manner. You don't pin yourself to something central that you then have to scale vertically versus scale horizontally.
Okay. So I do have a couple of quick questions for you. both in the chat and the Q&A here. The first question is, can you assign one container to multiple networks?
Yes. So as I showed in one of my slides, you can assign one container to multiple networks created by different CNIs as well. You just have to create those network definitions, the JSON network definitions, and when you call CNI, it will assign multiple interfaces that are part of multiple networks.
Okay.
Now, it is up to the orchestration system to decide if they want to expose that or not. So CNI, the spec, can do that, but then it's up to Kubernetes or Mesos or any of the other folks who are using CNI to decide if that's something that they want to expose or not.
Okay, so it's kind of a built-in feature that they have to then decide to make accessible.
Yes.
Okay. And you mentioned that in the new features with CNI, you have IPv6, which I think everybody thinks is exciting. How broad is support for IPv6 with CNI and like the plugins right now?
So IPv6 is generally well supported in the plugin side. On the plugin side, there's some lack of support on the Kubernetes side. It's not fully supported, but you can do IPv6 with Calico, with Kubernetes, and recently in 0.6.0 CNI release, they added a bunch more plugins in the IPv6 support. They added IPv6 support for a bunch of sample plugins they have on the repo.
I mean, I think one of the things I've been through multiple IPv6 transitions in my life at various operators, and the same thing applies here. The data path is actually reasonably well supported. V6 has been around for a long time. It's not that hard to do the data path. It's all of the orchestration, all of the OSS, BSS that has to catch up with it. So for example, some of the orchestration systems like Kubernetes may not have the concept of a V6 address for a service or something along those lines. It doesn't mean you can't use V6, but there's going to be some things that assume wrongly that all things are V4. And until it's that long tail of stuff that you have to clean up before you can say you're fully V6. But with CNI and a lot of the plugins, including Calico, all the plumbing's there. We're ready for it. It's just a matter of the orchestrators, the orchestration platforms catching up and making their infrastructure address family agnostic.
With Istio being such a hot topic, everybody's saying, look, we want to use, for example, Calico and Istio combined. Calico obviously works with CNI. How do we integrate Istio? Or does Istio work with CNI as well? Or? Sure.
Istio, at the end of the day, needs an IP network underneath it to work. Istio is dependent on IP transport coming out of the pod if it's a sidecar, out of the host. And that's exactly what CNI does. That's what the connectivity side of Calico provides plugged into CNI. So in order for Istio to work, it needs a network, and that's exactly what CNI and the CNI plugins provide. The more interesting thing, and we can talk about this more a little bit next week, is how network policy and Istio play together. And those actually are also fairly complementary, but we'll talk more about that next week.
With that, I'd like to thank Gunjan and Christopher for their time today and a lot of knowledge. I know I have a lot more digging into CNI that I have to do. So thank you again very much. And for me attending, thank you.
Thank you very much, everyone.